a topic which is different from the usual topics in this conference, though this time it's quite big with many sessions. I'll try and give you an idea of what we are doing in this field, and this, I would say, broadly falls in the quantum sensors thing. It's more related to quantum measurements. This work is done in my group at TIFR Mumbai. Primarily, I'm going to be presenting work done by Gaurav and Kishore. Suman and Nicola had started that work many years ago, and now Panya and Ishita are carrying forward the work which is going to be presented. More recently, we had a bunch of project students who have been helping with many calculations and simulations. So let me get started. This is the field connected to quantum bits. No. I don't know which one is interfering with what, but no, phone is over there. Yeah, possible. Yeah, so a superconducting or a quantum bit is essentially any quantum two-level system. The physical platform which we use is our superconducting electronic circuits, which are used to create these two-level systems. The simplest system we use is something which is called a transmon qubit. It's basically a nonlinear oscillator. You can see here a nonlinear potential well in the shape of a cosine shown here. And because it's nonlinear and not harmonic, the eigenenergies of this potential are not equally spaced, but unequally spaced, and that allows you to isolate the two lowest levels of this potential well as a quantum two-level system, and hence a qubit. But in principle, there are higher levels which are present, and one has to keep those in mind depending on the experiments one is doing. I'll comment on that later in the talk. The circuit drawn as a circuit diagram looks very simple. It has two components, a capacitance and something which is actually an inductance, but it's composed of this circuit element called a Josephson junction. A Josephson junction is a superconducting tunnel junction with two superconductors and a thin insulating barrier. And when you put two of them in a loop like this, you can actually tune that inductance by applying a magnetic field in that. But effectively just an LC circuit, but because it's a Josephson junction, the inductance is nonlinear, and the nonlinearity is of the same form as that of a regular pendulum. A pendulum is actually not a linear oscillator. It's only that when you have small angle of oscillation. When you have large angles, you have the restoring force being proportional to sine of the displacement. So hence, it has the same cosine potential in which it oscillates. So it's basically, that's why I like to call this as a quantum pendulum. So you have a nonlinear inductor shunted with a capacitor. Typical values of those inductance and capacitance are given here. That results in a resonant frequency, just 1 over square root of LC of around 5 gigahertz, which if you convert into energy units and then into temperature units using this relation, you get that corresponds to about 250 millikelvin. So this energy gap is very, very small, and hence you have to go to very low temperatures in a dilution refrigerator so that you can cool the system to its quantum ground state, and thermal excitations don't populate these higher levels, and you actually have control over preparing and controlling the states, which you do by applying microwave signals resonant with these transitions. Here's a picture of one such device. Right in the center, a zoomed SEM image shows the squid with two Josephson junctions. Here are the Josephson junctions, aluminum oxide, aluminum junctions, and then these two big pads form the capacitance. So that's basically what it looks. You can look at the size scale. This is almost visible to naked eye, nearly millimeter in size. And yet, under the right conditions, this can behave like a quantum mechanical object, showing effects like quantization of energy levels, quantum superposition, and entanglement. Okay. Now, the main topic here, which I'm going to be discussing, is the measurement of such systems. As you may imagine that, if you're using these superconducting qubits in a quantum processor on some quantum experiment, at the end, you want to know the quantum state in which the system has ended in, and because that is where you get the information. So knowing and measuring the final quantum state is very critical and is still an important challenge in many of these platforms, including superconducting qubits. To make that measurement, you actually take your qubit, which is a nonlinear oscillator, and you couple it to a linear oscillator shown here with a linear inductor. And you just basically, in electrical circuit language, you can just couple it with some coupling capacitance. And this interaction of a nonlinear multi-level system or a two-level system with a linear harmonic oscillator is similar to the cavity QED physics of a two-level atom interacting with light trapped inside a Fabry-Poro cavity. So the Fabry-Poro cavity is like your linear LC oscillator giving you a harmonic mode, and then your atom is like the superconducting qubit. And the interaction between these two is described by the famous Jaynes-Cumming Hamiltonian in this, which is basically here. So here you have your two-level atom, your harmonic oscillator, and the interaction term written as basically a photon exchange kind of process. But the regime we work in, we make sure that the resonant frequency of the cavity is different than that of the qubit, and that's called the dispersive approximation. So the qubit and the cavity frequencies are detuned, and it's much bigger than the coupling strength between the two oscillators. And in that regime, you get an effective Hamiltonian which looks like this, which again has your qubit part here shown as a spin half particle, but your cavity part, which is the harmonic oscillator, now gets modified by a term which is dependent on the state of the spin or the qubit. So what you end up having is that the resonant frequency of the cavity now depends on whether the qubit is in the ground state or the excited state. And that's actually the thing you detect. And you do that by basically doing a resonance measurements on the linear oscillator by scattering microwave frequencies close to the resonant frequency of this. And you can get responses like this. Which is showing you a response of the phase of the reflected signal as a function of frequency, and you have two resonant curves corresponding to the 0 state and the 1 state. And now by shining microwaves in the middle, you can measure a phase shift which tells you the signal. So that's actually the signal you measure, two different values of phase shifts in order to assign whether the system is in the ground state or the excited state. Here are some physical realizations of such systems. So this is called the 3D circuit QED because the LC oscillator is actually implemented as a three-dimensional waveguide cavity. Like this is showing a machined copper cavity here, and the resonant frequency is dependent on the dimensions of the cavity. And you put your chip in the middle, and the chip has the superconducting qubit, the transmon qubit. You can also make everything on a chip where both the qubit and the resonator are made in a transmission line or a lumped element model. And these are two different architecture. Most of the experiments I'm going to be showing use this 3D circuit QED approach. Okay. Yes?
How do you impute losses due to tunneling to higher energy states? Because you're only considering ground and excited state here with this cavity.
Yes, so we don't actually excite the system with too strong a drive so that you reach the excited state. But as you'll see in the process of the measurement, that can happen. Later on, I will talk about doing that. But under normal conditions, we don't expect the system to go to higher states because there's no energy available to do that. Okay, so since the task of identifying the qubit state is connected to measuring these phase shifts, it's basically that's the task you have to do. That's the engineering task you have to do. You just have to distinguish the two phases, and that depends on how much the phase shift is, how strong the signal is on which this phase shift is riding, the amount of time you integrate the signal to extract the phase shift, and then the overall noise levels in your system, right? So you can see all of this will give rise to how good this measurement is. So what you're seeing here is showing that when you measure a phase, it's actually not going to be a single value. It's going to be distributed around a mean because of noise in the system. And you need to make sure that this separation between the means is large compared to the variance of these distributions. And that's when you get a good signal to noise ratio, and you can detect without any ambiguity the two states. Okay. So this is again the same circuit. This is the Hamiltonian and the dispersive approximation. So I had mentioned that you can basically, the amount of signal to noise ratio, one of the quantities which depends on is the drive. So the idea is that you're now looking at these phasors in an IQ plane, basically the in phase and the two blobs here represent sort of the noisy signal, and the means are in the middle. And these two states are separated, shown as two different vectors. If you take a projection along one of the axes, you can draw these histograms. If I increase the amplitude, then this signal moves farther away while the noise remains the same, and hence you expect more signal to noise ratio. But when we do that, and that's one of the main topics here, we see that even though this Hamiltonian doesn't allow those processes, this Hamiltonian is an approximation. It's a second order perturbation, so approximation of the original Hamiltonian. And there are processes which can cause the qubit itself to change state because of the presence of the measurement tone. And that's harmful because you are now changing the state of the qubit and destroying the original information that is present. So you can cause ground state to become excited state or excited state to become ground state, which are shown by these little bumps here. And then you have ambiguity in knowing what the actual state is. So that's one thing. So you get the state mixing, which is a bad thing. You can also just integrate for a longer time because that will suppress the noise. So that will do something like this, where now the size of the signal remains the same, but now the noise block becomes smaller because you've integrated over a longer period. But these excited states have finite lifetime, so they can decay during the integration time if you do too much of that. So that can give rise to the excited state now having a little bump on the ground state, and that also can introduce errors. So you have to keep all of these things in mind and find the optimal operating point where you get the best SNR while ensuring that the measurement itself is not introducing errors by changing the state of the system you're trying to measure. Okay, so we are going to introduce a new circuit which is very similar but has a slightly different topology. This was the original circuit, nonlinear oscillator coupled to a linear oscillator. Here you can see the linear oscillator which is shown in red. Quite clearly, the nonlinear oscillator is connected in a different way. And the way it is connected is actually orthogonal in nature. What I mean by that is that any excitation on the readout resonator will not excite the qubit mode, which is with respect to this point and some virtual ground in between. So this orthogonality gives rise to some advantages, and this circuit is nicknamed quantum on. And you start with different origin Hamiltonians because of the circuit being different. But ultimately, you go back to the same effective Hamiltonian, which gives you this quantum state dependent shift, but it comes with different levels of approximation. In the original idea, you have to do these dispersive approximations and then reach there, whereas here, it's sort of a more direct step to go from the original Hamiltonian. And this is believed to be a reason why there are less spurious terms to worry about in this particular circuit, and that can help in driving the system harder, which can give you more SNR while ensuring that the qubit remains resilient and does not change state in the process of the measurement. This is not only the kind of circuit. There are lots of variants which have been studied over the years in many of these groups, mainly focusing on the measurement aspects. In our group, we looked at several other unique properties the orthogonal nature brings in, which is one is actually also protection from dissipation. Because of the orthogonal nature, any dissipation in the readout cavity, which is necessary to extract information, does not affect the qubit, so it's protected and can live longer. It also has this interesting property that the amount of frequency shift you get is somewhat independent between the choice of the two frequencies, which is not the case in this circuit. It depends quite strongly, so it gives more flexibility in using this. And we were trying to use this to get to high fidelity measurement without using low noise amplifiers in the system, which add more complexity to the cryogenic chain. It's kind of a strange thing because another side of our group does research on low noise amplifiers and how to improve them. And here we're trying to basically say that, can we get rid of those low noise amplifiers? And the basic point is that if I can drive harder, I don't need a low noise amplification chain, though you will always benefit in terms of reducing the integration time. Okay, so this is how it actually looks like in reality. So these big pads here are the capacitors. So, and here's the inductor for the resonator. And you can see now this is the capacitance of the resonator. The inductors of the resonator are shown are these little squiggly lines, and the Josephson junctions are right in the middle here, and they form a little loop. So 1, 2, 3 inductors, 1, 2, 3 inductors, a little loop here, and the Josephson junctions are there. And this whole thing is put inside a three-dimensional waveguide for measurements, and the signal here couples to these big antennas, and that's how we actually excite the system. Okay, so this is made of two parts, an aluminum part and a copper part for both low loss, and to be able to apply a magnetic field, because we need to tune the field in this superconducting loop so that it's biased at the right point. So this is, for example, how multiple chips can be placed in the same waveguide to measure more than one devices in a given measurement. Okay. So here's the experiments on one of device without using these low noise amplifiers called parametric amplifiers or param. These devices use tantalum as a material, superconducting material for the rest of the circuit, except for the Josephson junctions, which are always made out of aluminum. And these are those measurement histograms we obtained without using low noise amplifiers. And the fidelity, which basically tells you how much error you have in making a mistake. So for example, this histogram shown in log scale for the state 0, and this is the histogram for state 1. So you draw a line in the middle. So all the counts on the other side and the wrong side are your errors. So the fidelity is basically 1 minus the sum of the errors. And 98.3 fidelity, which means you only make about 1.7% error, is pretty good. It's not state of the art, but that's a good start for a system without using any low noise amplifiers. And this is done by integrating for about 1.8 microseconds and using about 30 photons in the readout cavity. Okay. And we also quote these other fidelities, which is basically how well the histograms are separated. So you see there is a green region here, which is about the noise related errors, and these bumps are due to the qubit state changing related errors. And you can actually separate that in these experiments, and that's important to know how much improvement in SNR you're getting and how much errors you are getting due to the qubits changing state. And these are just some parameters. Not so important, but we looked at how these errors change with integration time, and here the vertical dash line sort of tells you where we operated and found the best fidelity. So you see that as you increase the integration time, the overlap error, which is this green error, drops rapidly because now you're reducing the noise, but then after some point of time, the error, which is causing the ground state to come to the excited state, starts to increase, and that's just basically the qubit decaying. Because it has a finite lifetime, but the errors which are causing the ground state to get excited to the go to the excited state remain at least 1 order of magnitude low and increase only slowly. So this is sort of evidence that this system seems to be more tolerant to large photon numbers. And if you look at some of the other experiments we have done with this kind of a device, they all give us fidelities in the 97 to 98% regime. We have even reached close to 99 in some experiments, but when we use the conventional device without any parametric amplifiers, the fidelity is limited and about 4 or 5% smaller. So we see some evidence that this is actually giving us better resilience to photons, and hence you can drive it harder and maybe eliminate the use of low noise amplifiers, which will simplify everything. But so this is true that high fidelity is possible, but remember the integration time is about 1.8 microseconds. Typically, people want to finish these measurements in a few hundred nanoseconds. So using a low noise amplifier would help, unless we can increase the drive strengths even further. And that's sort of what the current line of research is. How do we play around with these parameters to suppress these qubit mixing errors even further? So this is a little visualization of what happens in these things. So these two blobs are the same thing. This is the signal corresponding to the ground state. This is the signal corresponding to the excited state. And as the animation is progressing, we are basically integrating the signal for longer and longer. And what you see is that initially these are nicely well separated, but you can see this little channel where basically the excited state is decaying into the ground state. But at large times, you also see there are some population getting out here, right? So what is that? If you now go to another experiment where we started by doing the experiment first by preparing the ground state, first excited state, and the second excited state. Remember, it's actually a multi-level system, and we can prepare this in all of these different states. Then you start seeing that in the presence of large number of photons and long integration time, you can get all kinds of behavior where the ground, the excited state mix with each other. They also go to other states which are not there, so which means that they're probably going to even these higher levels. So this comes back to your question that if you drive the system hard enough, some of these terms which are suppressed in the beginning, they get activated, and then the system can escape. And this is very bad. So we say that if the system relieves the 0-1 subspace, we call that leakage, and that also gives rise to error. So one has to understand all of this. This is a very actively pursued topic on figuring out what causes these transitions, how to change the Hamiltonian to suppress these, and our device is one such approach which allows you to do that. So these data shown here are at very large amplitude, which you usually don't work at, just to show that these kind of effects can take place. Okay. Now, we also are doing these kind of experiments in another type of qubit, which is called a fluxonium qubit, which looks like this: a small Josephson junction shunted by an array of large Josephson junctions and a capacitor. This large array of Josephson junction is used to create an effective inductance which is very large, which is not possible to do with geometric inductance because of stray capacitances. So you can do this, and this gives rise to a highly anharmonic qubit. So here the third level is no longer close to the first two levels, and that has some advantages. And again, we used a tantalum-based system. This was one of our best devices we have made, and also it's similar to, quite comparable to the state of the art in terms of combination of high coherence, about 400 microseconds T1 and 600 microseconds T2 echo time. And this was done with parametric amplifiers to get the best results. But again, we see that while we are able to get high fidelity numbers, and these are the same IQ phasors, you can see the ground state, there's a little bit of leakage to the excited state, but because we know the excited state is here, and then there is something else going on as well. So even though this is a very different system where the other levels are not so close by, even this system at sufficiently large number of photons can get excited to this. And the fluxonium qubit till very recently has been struggling to get high fidelities in these 90 and 95% and beyond. So our experiment recently was one of the first ones which showed a combination of good coherence and high fidelities. And of course, the question is how to take this further and how to improve it, because you want to ultimately make this number as large as possible to minimize the errors in your measurement. So 99.99 or maybe 99.999 would be the ultimate goal, and we still have a long way to get there. So we also looked at some other aspects of repeated measurements. So you do a measurement, wait for some time, you do a measurement again, and if the system behaves truly quantum mechanically, the result of the second measurement should be exactly the same as the result of the first measurement, because the system has collapsed to that eigenstate. But because of these effects of photons causing the system to change, you can actually get them to be not the case. So that number is called the quantum non-demolition fidelity. Basically tells you how much errors you're getting in this repeated measurement. And again, we showed very high fidelity, and you can see that there are very little bumps here, but there is a little a blip outside the histogram for the one state, which is again indicating that there is stuff leaking out of the computational subspace. So to look at it more carefully, we introduced what we called a leaked readout tone. This is just a measurement tone which is actually not carrying out measurements. Its job is to disturb the qubit. And then we look at what the final measurement is by starting the system in the ground or the excited state. We look at it as a function of this length of this pulse. And you see that in the beginning, you start in the excited state. When there is no leakage tone, it decays with an exponential and reaches the equilibrium state. The equilibrium state here is not zero because this is a low frequency qubit and there is enough thermal population. But when you start putting more and more power, the leakage level actually goes towards the excited state, which is almost looking like there's population inversion, but that's actually not correct, because this signal is contaminated by the signal of the qubit being in the non-computational states, which are higher, and that gives a signal which is erroneous. And we see the same thing happening for the system prepared in the ground state as well. Initially, it goes back to the equilibrium, but if you drive it harder, it goes to some weird state in the middle. So this is again evidence that even the fluxonium qubit with a very different level structure undergoes similar problems, and now there's a whole slew of activity around the world trying to understand these as well. And that's basically brings me to the last slide to summarize what we are doing and where we are going with this. So this quantromon is a two-mode circuit which is orthogonal and it's resilient to photons. And now we want to understand this system in a lot of detail using theory and numerics to figure out what is the correct parameter range where you can suppress these effects and get the best results possible. What are the limitations? We also want to use the fact that you can change the readout cavity frequency without affecting the performance to utilize the full measurement band, which can reduce the requirements of wiring in a multi-qubit system, and then ultimately integrating this into a more compact 2D circuit QED where everything is on chip for scalability. And this work is being now carried forward by PhD student Ishita and then other project students who are helping with these simulations. And same kind of idea with the fluxonium, which is a low frequency but a highly anharmonic qubit. And again, we have started doing extensive numerics following other work done around the world to understand why our device seems to be doing better than some of the other ones, and then further fine-tuning the device parameters to demonstrate even higher fidelity and maybe even possibly without using low noise amplification techniques. And again, for scalability and other things, we want to move to the 2D circuit QED architecture. And this work is being led by Panya Jain and project student Kishan Bhuvan. So with that, let me thank you. Here's a picture of some of our group who have been around for various years. These projects have been going on for quite a bit of time. So I will stop here and take questions. Thank you.
Thanks, Vijay, for the very illuminating talk. The session is also for questions now. Yes.
How this fluxonium is different from the transmon?
Yeah.
How this fluxonium and quantum is different from the transmons?
So the quantrumon is a variant of the transmon in the sense that it's also a weakly anharmonic oscillator. The difference between the quantrumon and the transmon is that the way the qubit and the cavity mode are coupled to each other. So that gives rise to a different starting Hamiltonian, even though the final Hamiltonian which we're using for measurement is the same, but in the quantrumon you are throwing away less terms, so there's less things to worry about when you drive it at harder. So it's the same qubit type. There is a different history for why we have called the quantrumon, I can tell you offline.
Sir, one more.
The fluxonium is a very different qubit, even though it looks very similar in terms of a junction and a capacitor, but this junction is much smaller, which means it has much higher inductance, and there is a very large inductance which is shunting it. So you have a cosine potential coming from the Josephson junction and a parabolic potential coming from the linear inductor. And these two combine to give you a very specific situation where you have two degenerate states which are tunnel split and hence give a very small frequency. So if you remember, transmon qubits had 5 gigahertz frequency difference. A typical fluxonium qubit has around 300 or 200 megahertz splitting. And that protects the system to some extent.
And what are the software tools you use for the Josephson junction designs?
Software tools. I mean, the Josephson junction is just two rectangles sort of top of each other. So standard CAD tools, they are written using an E-beam writer.
And circuit level simulations?
HFSS, COMSOL, Keysight ADS, all of these we have been using.
So do you fabricate these devices in your lab or?
Yes.
Thanks.
Yeah.
Okay, Satyajit.
What is in your quantrumon, what is the decodance time scale?
The decodance time scales of our quantrumon devices is typically around 40 to 50 microseconds. Though some of the best ones we have measured have reached close to 100 microseconds.
What is the purity of the aluminium that you use?
The purity of the aluminum?
Because I believe they have to be highly pure so that the quasi-particle sort of poisoning.
So can you please use the microphone?
Yeah. So what he's asking is what is the purity of the aluminum we are using? So I mean we buy 5-9 aluminum and use it, but that is the easy part. The impurities in the aluminum, as long as they are not magnetic impurities, is not usually a problem in this case. In fact, the aluminum is sort of as a dirty. Sometimes in some experiments we deliberately introduce additional oxygen to do gap engineering to move the quasi-particles away from the critical parts of the devices.
One small. Can I ask?
Yeah.
I'm sorry.
You want to come back? There is a.
Yeah, thank you. So there was this box which you showed where you said that you use it so that you want to also use a magnetic field in there.
Yes.
Can you give some numbers on, because I thought magnetic field is detrimental to these things, and
yes.
then you have
So
magnetic field.
in general, magnetic fields are bad for superconductors, but those fields are much higher. So that depends, of course, on the superconductor itself. These are very small fields whose job is only to introduce about a flux quantum in the loop.
Yeah.
And they are only activated after the system has reached. So we don't cool them in a magnetic field. We in fact use a lot of magnetic shielding because this is just a superconducting coil.
So you just put in a coil there to and pass current.
Pass current
Yes, okay.
once the system is at base.
Okay, last question by Anjan.
I was curious, this decoherence time or whatever,
Yeah.
is it extrinsic or there are intrinsic factors also?
They are both. If you have done your job correctly in terms of your design, you will suppress all the extrinsic factors. So, for example, because the cavity has to be coupled to a microwave feed line, that can give rise to dissipation. But if you design the frequencies and the coupling carefully, you can make that number insignificant. Ultimately, for a well-designed qubit, the decoherence times are set by microwave frequency absorption happening in the circuit. Usually in the dielectric, it could be oxide layers on the surface of the superconductors, defects in the superconducting material in the interfaces between the substrate and the metal itself. So over the years, people have improved. So I remember, if you remember, I said that we moved to tantalum because a few years back, tantalum was shown to have much thinner oxides, which seems to have less losses at microwave frequencies. But if you design your chip or your enclosures badly, then you will be decaying into unwanted modes.
But what I wanted to say was, you take a machine perfect. Will there be an intrinsic limit also?
Yes, the intrinsic limit is related to the materials. So it's not, it's not like a fundamental limit. It's a limit connected with the processes you are using. And again, you can do the same processes in two different labs and they will be different. Usual stuff.
Okay,